And I think that's all I need to do. I feel like every time I set this up, I'm missing something. Recording, slides are good. I'm on the call. I think that's it. I have 2 minutes still. Okay. This is going to be a quiet tutorial. How are sequences going?
Might have paid some attention to the lecture.
Sure. That's very reasonable.
I have an idea of what they are.
Mm-hmm. Oh, hello? Is that looks like Marion's pink color on Discord. Cool. There should be a chat box feature in this. I think. Yeah. You have no sound. Is that my end? I don't think it's my end because my box is. Oh, you can't hear me. I don't think it's my end. My green box is showing up. There we go. That should be somewhat clear. Always troubleshooting, always something wrong. Hate tech. Do you have Discord like on your phone?
Yeah.
Are you able to log in and just see if I can? Because I don't know if it's on Marion's end or if it's on my end. But like audio. I assume the video is working. Testing? Yeah, it's working. Awesome. So.
And the video's
Video's fine? Cool. All right, keep trying. Figured it out. Cool, great. Okay. As long as it wasn't on my end, I don't really care. Okay. In that case, we'll get started, and I'll make sure I actually am recording, which I actually am. Great. Okay. So we're going to talk about sequences. So sequences are pretty much straightforward, I think. Usually you denote a sequence something like this. Maybe you've seen it like this, or like this, something like that. Or if you really want to abuse notation like this, they're all sequences. They're all different ways to write them. I usually use, I don't know, I don't usually use that. I usually use one of these, usually one of these. Yeah. So sequences are, and I think I talked about this last week, sequences are functions from natural numbers to, in this case, if we're talking about real sequences, natural numbers to R. Yeah. So that's sort of the long and the short of what a sequence is. It's a function. It takes in a natural number and spits out some real number that's associated with it. There's a few key properties with sequences. One of them is, well, boundedness. So a sequence is bounded if, how does this go? For all n natural numbers the absolute value of an is less than or equal to m for m positive real. Does that look right? Something along those lines. So you could write this as like negative m is less than or equal to an is less than or equal to positive m. That's where that absolute value comes into play. And that works for all n. So you need to find like a bound for every possible n. Another one is convergence. So, and this is one of those things that I just suggest you repeat again and again and again in your head. Maybe I'll put it up here so that you have room. For all n natural numbers, I'm getting this backwards, sorry. For all epsilon greater than 0, there exists an n natural number such that for all n greater than or equal to big N, xn minus a is less than epsilon. So if this is true, if for all epsilon greater than 0 there exists an n such that for all n greater than or equal to big N this holds, then we say that xn converges to a. So then I guess you should technically write as n approaches infinity. Yeah. But this is like the thing, sort of this piece here is really what you should memorize and just say it again and again and again so that you have that down pat. Because I think writing that will give you like half the marks already, just because it's like, you know, that's usually the spot that people struggle with. And I'll turn this so you can sort of see the last bit of that. Yeah, so that's pretty much it for series. Sequences. Series, of course, is the sum of sequences. So I don't know if we've really, well, we talked about that last week a bit, but I don't think we're going too far into it. Go on to question 1, and maybe I'll see if I can turn off a light so it's easier to see. But
Yeah, I just turned them all on when I came in because it was pitch black.
are they on this?
There.
They're on the door. Of course they are. Is this the right one? Looks like it. Oh, that was this one. This one. There we go. That's what I wanted. Okay. Maybe that'll help with glare too on the, a little bit helps with glare. Cool. Yeah, so we'll get started on question 1. Which of the following statements are true and which are false? Prove the true ones, provide counterexample for the false ones. Pretty straightforward. I came a little bit more prepared today than I usually do. So I have all the answers.
Oh,
It's not, I don't usually do that. But
I'm lucky enough with my tutorials, I just get the answers given to me, so I don't really have to do much solving in front of the class.
yeah,
So
it's,
I always, like, I miss a negative, or I add things wrong.
it happens a lot. So once you move past first year, the way it typically works is instructor sends you an email the night before your tutorial telling you what they covered, and then you make all the questions and make all the answers and figure out how you want to organize it all. And that's the hard part. Yeah. That gets frustrating sometimes. Especially, well, I shouldn't say that. Some professors are very late at telling you things.
Mihai?
No.
Oh, not Mihai. Wow.
If it was Mihai, I couldn't say yes.
Oh,
But-
right, because you're taking for Mihai's courses this semester.
I am, and I'm recording. But no, there are some profs out there who just will send you random stuff at like if this tutorial's 2:30, you get an email at 1:30 saying here's what we did. I'm like, okay,
You just have to leave the whole thing at that point.
pretty much. It's happened before. It's happened before. I don't think Mihai's ever done anything that bad. I've had worse.
The only thing Mihai does is finish exams like right before we're about to take them.
Hmm?
Like he walked into our differential equations exam, like final exam,
Hmm.
I think 5 minutes late because he was still printing the exams.
Nice. Yeah, that happens. All right, question 1. Let's see if I can move this back at all. A little bit. I just want to give you a better view of the board so I can use more board space. That's not too bad. Okay, so I can go from here-ish to here-ish. All right, so we'll take up question 1. Hello? No? Okay. Nobody wants to do real analysis. Sad. So question 1 is if x converges, if x n converges, then xn over n converges. True or false? Any idea?
True.
True. It is true. Any idea of a proof?
I said that, so suppose xn converges to some real number a.
Sure.
So as n approaches infinity, xn approaches a.
Yep.
Then xn over n as n approaches infinity would become a over infinity,
Yep.
which would be 0.
8 over,
Or when
N,
approaches
yeah.
0, not equal to 0.
so this approaches some number over infinity, so 0. Yep. Yeah, exactly. That's exactly the proof I did, I think. Yep. 2. Is sort of the opposite of that. If xn diverges, then xn over n diverges. Not converges, diverge. Any ideas?
False.
It is false. Counterexample, what should xn be?
I said sine of n, but there are simpler examples.
They're way simpler
Like
examples.
we do, I think, -1 to the n.
There are way simpler examples.
Than that.
Yep.
N.
Yep. N diverges. Xn over n is equal to n over n is equal to 1, which converges to 1. But yeah, you could do sine, but then you're involving like, was it L'Hopital's rule or something?
I mean, I guess, but I don't think you are technically allowed to use L'Hopital's rule for sine n over n.
For sine n over n. Yeah, you are.
Are you?
Think so, why not?
I saw it, I've seen it before that if you try to do L'Hopital's rule, you're kind of using circular reasoning, cause when you try to take the derivative of sine x,
Mhm.
by first principles, you end up with basically sine h over h, I think. Or something.
That's a fair point, yeah, you're probably right. I feel like there's a way to do it without that, using properties.
I said that it's because sine of n is bounded.
Sine of n is bounded, so
Right,
bounded
between
over,
-1 and 1.
yeah, so,
Which means you have some number between -1 and 1 over.
so
n
you're
plus
using
n.
squeeze theorem almost, right?
Yes.
Because you're doing 1 over n times sine of n. This is bounded, this goes to 0. So it's like a squeeze of like, whatever, you know the squeeze theorem. I'm not good at drawing it, but
Yeah.
you get the idea. I don't think we've covered squeeze theorem yet.
No, that's from calculus.
Yeah, we're gonna do it rigorously.
Oh, okay.
Yeah. But yeah, when you're trying to come up with examples, pick easy ones, as easy as you can. Question 3. True or false?
False.
Let me just check the chat and see if there's anything.
No, that's true.
That is true, yes. So, let's see. So the question was, if xn converges and yn is bounded, then xn, yn converges. Yeah. So it's the proof that I have for this one. So if xn goes to L, as n goes to infinity, and let's say yn is less than or equal to m. So by definition of convergence and bounded, then we can say xn yn minus lyn goes to 0 as n goes to infinity. And I think that's just definitional convergence if yn is bounded. Make sense? Question 4, or part 4, I should say.
I'm saying false.
It is false. You have a counterexample?
Xn is 1 over n, yn is n squared.
Yep, that's exactly what I got. So just to write the question down, it was xn goes to 0, and yn is greater than 0 for all n. Then we want to show from this that xn, yn converges. It's false. Yn is greater than 0 for all n squared is always positive. Xn is equal to 1 over n, that does approach 0, but then xn, yn is n squared over n, which is n, which does not converge. Any questions in the chat? Any questions from you? All good? Cool. Okay, let's go on to the next one. Question 2 is a proof. It's a hard proof. It's a big proof. Suppose that, I'll write this down. Just want to make sure it's all in the video. So suppose xn is a sequence. I should probably write it using keep notation consistent. There's another way to write sequence in R. You know what it is?
Will you write it with the function notation?
You could. The way I was thinking was that.
Yeah, that's what I meant by function notation.
Sure, yeah,
I wasn't sure
sequences
exactly what
in
they're
R.
called.
Yeah, it's all good. You could also write xn maps n to R.
Actual function notation.
Actual function notation, yeah. Although that's kind of a weird way to write it, because like, that's not really a function, right? It is, but it isn't. Yeah, so we want to suppose that, and then show, so we want to show that xn converges if and only if all subsequences of xn converge. Have you guys done subsequences yet?
Maybe.
It's natural, right?
Yeah.
And we're talking infinite sequences and infinite subsequences.
Yeah.
So there's not really a notion of finite here. Awesome. Gonna give a good chunk of time for this. Or at least until you and Marion are done.
I'm trying to remember the definition right now. I know it's,
Of conversion?
yeah, I'm struggling to put it down on paper.
It's
Like intuitively I understand it, but that's not enough, right?
it's not. For all epsilon greater than 0,
Yeah.
there exists an n
There it is.
natural number such that for all n greater than or equal to n, absolute value of xn minus a is less than epsilon.
Eventually you'll be able to see that in your sleep,
It,
but
it's very similar to the epsilon delta definition of the limit.
yeah,
Wait, are we doing that, I suppose?
yeah.
I figured.
We're doing everything from Calc 1 using epsilon delta. It's gonna be a pain.
I expected to be doing it in Calc 1,
Yeah.
but we didn't really do the proofs. We just kind of briefly touched on it, and they had us like
Yeah.
picking actual numbers.
Yeah, that's what you really do. This course, you're gonna do actual proofs
Yeah.
of like epsilon, like definitions of, well, limits, convergence, we're doing, derivatives, integrals. I think that's it. I think we stop at integration, like basic integration.
Yeah.
Maybe we do by parts. I think that's about it. Derive those formulas. If Mihai were teaching it, we would get all the way to like in Green's theorem and stuff. Deriving those formulas by hand.
It was fast.
Oh yeah. Oh yeah. How's it going, Marion? All good. All good. Any questions I can help you with? So far, trying to wrap your head around convergence. Yeah, so I think you've seen it, but you're not really expected to have seen it a ton in the rest of your degree. But really, the idea with it is that, so I'll write out the definition and then I can sort of talk through it. So for all epsilon greater than 0, there exists an n natural number such that for all n greater than or equal to n, absolute value of xn minus a is less than epsilon. So this thing here is the same thing as saying xn, some sequence approaches a, as n goes to infinity. So, okay, so what does this mean? So for all epsilon greater than 0, what we're talking about is that you can pick a super small real number, however arbitrarily small you want, as long as it's bigger than 0. So you pick like, you know, epsilon is like 0.00000001, however small you want. No matter how small of an epsilon you give me, I can come up with n, which is a natural number. So this is like an indexed limit. So we have this sequence xn. We want to show that as time goes on, if you keep plotting that sequence, and maybe using a line is not a good idea, but if you keep like plotting this sequence, that it eventually is going to reach some like limit. It's going to converge to some point, as opposed to like shooting off to infinity or something. So in this case, we have, there exists an n in n. So basically, no matter how small of an epsilon you give me, I can pick some natural number. It might be a really big natural number, but I can pick some natural number such that for every index past that natural number, the difference between the point that I'm at and this dotted line, which is a, is smaller than that tiny, tiny number. So, for example, maybe like epsilon is some value, this is a, and these dots represent like my sequence xn. Maybe the big N value is here, so that after this big N value, every point that comes after it is going to be within epsilon from that limit. So that's the idea of convergence. Is like as you get closer, it gets closer and closer to that line within some like tolerance epsilon, some like error amount epsilon. And it does that for every value after some natural number, after some point. Hopefully that makes some sense. That's convergence. Awesome, I'm glad. Yeah, so what I was saying is like, try and memorize this like, for all epsilon greater than 0, there exists an n in n such that for all n greater than n, the absolute value of xn minus a is less than epsilon. If you just memorize that formula, that's like half the battle. Do you have one direction done?
No.
No? Okay.
I'm working on, assuming every subsequence converges,
Okay.
showing that the, main sequence converges this result. which
Okay.
Intuitively makes sense to me, it's just finding a way to
Yep.
actually prove it.
It's tricky. I'll just start on one direction here, the forward direction. So the forward direction is we assume, suppose xn approaches a as n approaches infinity. And we want to show that every subsequence x n, well, there's a few ways you can write a subsequence. That's one way. And what do I want to say? Converges. Depending on how you're writing subsequences, or how you're writing your main sequence, if you have like xn for all n in n, you can have a subsequence of that which could be like xm for all m in some set, say E, which is a subset of n. And I think you need it to be, well, the strictness of that is ambiguous, but yeah. Want to show every subsequence is convergent. So let's see. So we'll just consider this subsequence. I think there's like a better way to show this, which maybe I should do. So we know that for all epsilon greater than 0, there exists an n natural number such that for all n greater than or equal to n, x n minus a is less than epsilon. So we have that. So it's also true that for all epsilon, there exists an n such that for all n, and using this n and this n are actually the same, as long as the epsilons are the same. Right? So basically the argument I'm making here is that, say that like your subsequence was like every other point, just as an example. There always has to be infinitely many points in the subsequence. So if it was every other point, and let's say that the n value that we had from before was like there, right? So what we're saying is that for the normal sequence xn, the full sequence, this distance here is epsilon. So like the distance between the point and this limit value a. And I'm drawing this really poorly, but I think you get the idea. Anyways, so after this n, every point in the original sequence has to be less than that epsilon amount of error. So that means that it has to be fulfilled for some subsequence, right? So like even if it was every other, like after that n value, every other is still gonna be less than n if everything is less than n, or past n is less than epsilon, right? So from that you get, what do you get? You get x and k approaches a for any subsequence, because we never really defined what the subsequence was. And then the other direction is, I think, a little bit harder, but not too bad still. So the other direction let's suppose, did you end up getting it? Hi.
Not a very good proof, I don't think.
So let's suppose that, for sake of contradiction, that xn doesn't go to a. Then there exists epsilon naught greater than 0, such that for all capital N in N, there exists an N greater than or equal to N, such that absolute value xn minus a is greater than or equal to epsilon naught. You see how I got that chain of quantifiers?
Just the indication of the definition.
So like if for all became a there exists greater than, there exists here became a for all. The for all here became a there exists. And then we negated the inside statement. So what does that mean? That means that infinitely many terms are at least epsilon naught distance away from A, right? So you have infinitely many terms, that's this for all n in n. There exists in n, so you can always keep finding infinitely many terms that are at least epsilon naught distance away. So what does that tell us? So from here, let's say, let x and k be a subsequence of xn. How are we defining this? So we're defining it such that x and k, so it's a subsequence such that x and k minus a is greater than or equal to epsilon naught. So we're just sort of pulling out all those infinitely many points, right? Because we can do that because there's infinitely many of them. Yeah. Such that this happens, this works for all k. However you want to describe that nk. So every index of this subsequence has that distance greater. If you have that, then what this means is that x and k does not approach A, which I believe is a contradiction. So xn must approach A. I think that's right. Yeah, I think that's right. Does that logic make sense? Did I make a mistake?
The logic makes sense. I'm just struggling to follow it on the page or on whiteboard.
Sure. Yeah, so,
So that one, we're trying to prove the, like, right to left direction, right?
we're trying to prove the right to left, yeah.
Yeah, suppose every subsequence converges.
Yep.
I wanna show that X converges, so we start with the assumption that it doesn't converge and show that must be correct.
Yep. Yep.
Because we get that if XM doesn't converge, there's some specific subsequence that doesn't converge.
Exactly.
But we assume, yeah, okay, yeah, I'm following.
Yeah. Awesome. Any questions, Marion? I know that was a bit of a difficult one. I hope when my chat's open you can still see the, yeah, I think you can still see. Hearing the other question made it make more sense. Great, I'm glad. Yeah, sometimes it's hard to explain, and then once someone else explains it, it makes it easier. Okay, we'll go on to question 3. Last question. It's a bunch of proofs. You can change limits to
Yeah.
convergence, converging values. I don't know.
Is it like kind of the same definition? 'Cause
Simple,
They look very similar, the only difference is the
sided.
delta part is missing.
The delta part is missing. Yeah, it's the sidedness of the limit.
Yeah,
Yeah, I think that's the key difference.
yeah, and that's where you need the delta part to cover that, right?
Exactly. Also because we're dealing with natural numbers, right? As opposed to like a limit of a function, which is like,
Yeah.
you know, or a continuous real number function. Limits are sort of just more difficult and more generalized. So what I'll do is I'll erase this. So these questions are, and I don't think you've done these. I assume you have not. The first one is that if xn goes to A and yn goes to B, want to show that xn plus yn goes to A plus B. So you can add convergence or converging limits. If xn goes to A and C is a real number, I want to show that Cxn approaches Ca. 3 is if xn goes to A and yn goes to B, then xn yn goes to AB. And last is if xn goes to A and yn goes to B, then, and I guess B is non-zero, then xn over yn goes to A over B. Which question?
One.
Two epsilon.
Yeah,
But that should be fine because given the initial assumptions are true for any epsilon,
exactly.
you can just take epsilon over two.
Yep, you got it. Yep, that's exactly right. I just would have taken epsilon over 2 right from the start. But that's one of those like draft it and then redo it.
Yeah.
Yeah. So yeah, exactly. Since you can pick, you can pick epsilon arbitrarily small, so you can pick 2 epsilon arbitrarily small, right? There's some argument about sequences and convergence about that, which is not very good. It's kind of annoying. Now we can do that one sort of together. Just get it up on the board. So for one, as n approaches a, is the same thing as for all epsilon greater than 0, there exists an n natural number such that for all n greater than or equal to n, absolute value of xn minus a is less than, and I'm going to do epsilon over 2. Since you can pick it for any epsilon, we can pick it for any epsilon over 2. And we'll do the same thing. Also, yn approaches b means that for all epsilon greater than 0, there exists an n natural number such that for all n greater than or equal to n, xn minus a is less than epsilon over 2. I think that's right. So then for n greater than or equal to the max of n, and I should really give these names here, n1, n2. So n bigger than the max of the 2, we get xn plus yn minus a plus b is less than or equal to, is that right? Yeah, less than or equal to xn minus a plus yn minus b. This is just from the triangle inequality. And so from there, this you can, is this right? Yeah. This is strictly less than epsilon over 2 plus epsilon over 2. So it's less than epsilon. So xn plus yn converges to a plus b. I think that's roughly how you did it. I think you might have missed a couple small nuances there. The first key one I think was that n has to be bigger than the max of the 2 n's that you chose for your definition of.
Oh, yeah, I can't say that they're both the same then.
Exactly. You could say that they're the same epsilon, but you can't say that they're the same n. Because it works for all epsilon, whereas this there's a specific n. Yeah. So then from here, the other thing is, I don't know if you did you do the triangle inequality to split those up? Or did you do it a different way?
No, I like decomposed the absolute value
Okay.
and then added them. Like added the equations.
Okay,
and then
that's probably fine.
Reformed the absolute value
That's probably fine, yeah.
from the definition after the like rearranging was done.
I just did triangle inequality. So I started with sort of where I wanted to end up,
Oh,
xn
yeah.
plus yn minus a plus b. Separate that using triangle inequality. And And then this has to be less than, since n is greater than or equal to the max of the two, this has to be less than epsilon over 2. This has to be less than epsilon over 2. So they have to be less, added together, have to be less than epsilon. So it converges. Number 2, did you do number 2?
Working,
The constant multiple?
yeah, getting put up by, C less than 0.
C less than 0. I hope I didn't make a notational error. I'll write down what I have in my proof and we'll see if it works for C less than 0. So I have for all epsilon greater than 0, there exists a natural number such that, let's see, for all n greater than or equal to big N, natural numbers n. There's too many n's involved here. Xn minus a is less than, what did I do? I did epsilon over absolute value of c. Again, same argument as before with the 2. So from here, what do I get? So for all n greater than or equal to n, we get that c xn minus c a is equal to absolute value of c times absolute value of xn minus a, which has to be less than absolute value of c times epsilon over absolute value of c, because of this, which is equal to epsilon. I don't think I relied on,
No, I was doing the same thing where I like get rid of the absolute value and then try to kind of build it back up
sure.
rather than working within it. Like
Oh,
that.
sure, I see, yeah.
Um,
Makes sense, that's fine.
so
Either way
that's-
should be fine.
That's when you multiply by the C.
Yeah,
And I'm switching around the inequalities. I think it still works out, I just
probably does.
haven't worked it out on the paper.
It's just all those inequality laws and absolute value laws, right, that are kind of hard to remember. Like this one,
Yeah.
right? This is one of those like, oh yeah, you can pull out the C in an absolute value, right? And yeah, it's kind of ugly, but it works. So because we showed that this is less than epsilon, that means that C xn approaches CA as n goes to infinity. 3 was, what was it? Xn goes to A, Yn goes to B, then Xn, Yn approaches AD. How did I do this? I think I did this one a little bit differently. I think. We start with this. You can expand this as Xn, Yn minus Ayn plus Ayn minus AB, which is less than or equal to absolute value of xn minus a times yn plus absolute value of a times yn minus b. So this is using like triangle inequality and the pulling out a constant multiple of from a thing, right? So sort of factoring this into 2 separate terms. Triangle inequality, pull out the common factor of yn, pull out the common factor of a. And then from there, since we know xn goes to a and yn goes to b, then xn minus a has to go to 0, and yn minus b has to go to 0. And you could think about that in terms of 1, or you could think about that just logically. So what do we get from that? That means that this term is less than epsilon, and we could like go through and sort of define this a bit better, right? So we could say, maybe a better way to do this is to go here and say like the whole argument for all n greater than or equal to n should probably start with for all epsilon greater than 0, there exists an n natural number such that for all n greater than or equal to n, and I should name these like n1 maybe. So in that case, we can get xn is equal to, xn, absolute value of xn minus a is less than epsilon over absolute value of yn. Again, we can do that for any, yeah. Same thing as up here. And then we can do it again for all epsilon greater than 0, there exists an n2 natural number such that for all n greater than or equal to n2, not x, y, n minus b is less than epsilon over absolute of a. And then I think if you plug and play these here, going back to this, you get that this is less than, well, strictly less than epsilon over, and maybe I should put 2's here, epsilon over 2 absolute value of a plus, or times absolute value of a plus, I got this backwards, didn't I? Should be yn over yn plus epsilon over 2 absolute value of a times a. These cancel, you're left with epsilon over 2 plus epsilon over 2, which is epsilon. So because this is less than epsilon, then we get x and yn converges to AB. And just enough time for the last one. The last one's actually really easy, given 3. Just say that, so xn approaches A, yn approaches B, and B is not 0. Then we can say that Zn is equal to yn inverse, and that inverse exists because B is not 0. So then by question 3, we know that xn, Zn approaches A, B inverse, which shows that, yeah, xn over yn is equal to A over, or approaches, sorry, A over B. So you just apply 3. There might be some argument needed here as to why yn over B approaches, sorry, yn inverse approaches B inverse, but it's sort of more logical, straightforward. Yeah. Make sense?
Yeah.
Cool. Marion, any questions? I know that was a lot. It's a lot of convergence and a lot of absolute values and stuff. That's annoying, eh?
Put a sign on the door.
I should. So far, good. The repetition helps. Great, I'm glad. Yeah, the repetition should help. Just keep repeating. For all epsilon greater than 0, there exists an n natural number such that for all n greater than n, absolute value of n minus a is less than epsilon. If you just keep saying that again and again and again, it helps. That's what I did when I took this course. Just repeat it.
I'm going to pair of headphones and wear while I sleep.
Exactly.
People learn languages.
Yeah, there's I don't know if you've seen it, but there's a good not that like you have to do this by any means, but there's a really good resource by, what's his name? Oh my god, I can picture him. He's on Udemy. If I just Google it, I hope not.